We're going to talk about private cloud compute and hopefully what I learned trying to build something similar at Confident Security. But since Apple's private cloud compute is oriented around consumer AI on devices, I wanted to first kind of motivate privacy and security for this audience. Maybe everyone here believes in privacy. Actually, a show of hands, who cares about privacy? Who here thinks consumers care about privacy? Okay. And who cares about privacy has submitted their data to ChatGPT? That's actually pretty good. This is an aware audience. Okay. So this is just like the motivator for a great AI example. DeepSeek data leak exposes a million sensitive records. This is going to keep happening. It's happened many times before. But I think things are even heightened with AI and people are more concerned about it. Enterprises, on the other hand, actually do care about privacy and security, right? Healthcare, fintech, legal, there are financial consequences to not keeping data private. And AI has increased those concerns, and I think primarily because of data training and like who owns the data and like who's getting a lot of value out of that data. And so in the enterprise, you pay for single tenancy, on-prem, bring your own cloud, all of those things. And that helps you get increased security and privacy guarantees. But that's not as easy with AI because no one's going to just go buy an H100 for their medium-sized business or startup and like spin it all up themselves. So it costs even more to buy security now with it unless you want to like run a whole cluster of H100s. And that's really what Apple was trying to fix. So they wanted to have AI available to their consumers. Those consumers only have a small amount of compute on their phone. But privacy is a major selling point for Apple. We can haggle about whether it's a marketing point or a real point. I think it is a real point. But anytime you're asking your customers to give their data to you, they're inherently giving up some of their privacy. And so Apple built this thing called private cloud compute that powers Apple Intelligence. Came out in October, and Apple Intelligence came out. Apple Intelligence kind of flopped, but whatever. So this talk will primarily be on exactly how Apple private cloud compute was built, and hopefully for you watching, you'll either learn something new or know what questions to ask if you encounter this professionally about data privacy, because I'm sure for some of us work for businesses do care, and then maybe personally you might also care. So kind of quick disclaimer, I've not worked for Apple, I'm not speaking on behalf of Apple, please don't sue me. Everything that follows is gleaned only from public sources. Okay, so this is the fundamental problem that Apple went out to solve. I have an iPhone, I want to have it send data to a remote, untrusted server. And how can I make that remote trusted server, make that remote server trusted? And also that the remote server should also be hard to hack. And so that's what private cloud compute does. So for the rest of this discussion, I'm just going to say client rather than iPhone, but I think it's a stand-in for an arbitrary client submitting data to a much larger AI system. So Apple set out and they create 5 key requirements for private cloud compute that kind of set the stage for what they're trying to deliver in terms of privacy and security. The first requirement is stateless computation. This idea that when you send the data to Apple, they only use it exactly for the request, nothing else. Must not be retained, must not be logged, can't be available for debugging, can't be trained on. It's used for the life cycle of the data, the request that they received and satisfying the request, and it's gone. The second principle that they have is enforceable guarantees. And these are exact quotes, just to be clear. Code is that everything is done in code, not by convention or policy. So things like if you don't want people to be able to log into the machines to see the data that's being sent to those machines, don't have SSH available. If you don't want to log the data to disk, don't have a disk available, right? So these are enforceable things rather than just some policy that says, oh, no, we'll do the right thing. Next principle that they have is non-targetability. An attacker cannot compromise data that belongs to specific users without a broad compromise. So that it's essentially like you have to hack all of Apple, not just one specific machine on Apple's servers. No privilege runtime access, we talked about this before, but there's no way to override the privacy guarantees that they've coded into their system for any reason. And the last one is the most important one, is the verifiable transparency, which is the ability to verify all of these other requirements are met, right? In particular, the notion is like if you're a security researcher, you can exercise Apple's system, see that it's meeting these guarantees and these requirements, and then when you run the system, you can see that the running version is doing exactly what you had verified offline. And we'll get into how they do that. So to start, I want to give like a high-level, kind of abstract conceptual overview of how they meet these 5 requirements, and then we'll dig into the 6 components that they use to like technically meet them. So the first thing that they do is that they add an anonymizer into the front of the whole call stack, right? So if you're on an iPhone and you're making a request to Apple's servers, the first thing that Apple can't do is they can't identify where the traffic came from and who they came from. But an anonymizer isn't great alone because auth still happens after anonymization. So great, they anonymize my IP address, they anonymize all the metadata, but then there's an auth key in the request that can identify me. So the first thing that they do is they move auth out of the main path of a request. So the first thing you do is you go to some auth server at Apple, and you say to that auth server, here I am, here's my identification, and Apple says, great, here's some coins, like almost like you're at the arcade. Here's some coins you can go spend. And then you say, great, thanks so much for these coins. And then I send my actual request through an anonymizer. The anonymizer is a third-party service called either Cloudflare or Fastly in Apple's case. They kind of launder the data with this little anonymous token that they got, and then it flows through. So now there's no targetability. We have no metadata about who the user is in any way, shape, or form. So now someone has to compromise the entire system if they wanted to target you. Okay, so the next thing they do, I'll add is verifiable transparency. So they add some additional steps before the request to verify what Apple's is running. So the iPhone, through the anonymizer, says, hey, Apple, tell me what code you're running. And it responds, yeah, I'm running this code and that code. And then the iPhone says, great, if that remains true, here's my data, and you can run as long as you're still running the code that you promised me before. Of course, this is a very lofty claim. I think everyone here might be like, well, yeah, but you could be lying. So we'll get into how they can prove that they're not lying in a second, but conceptually this kind of flow happens. And this is the verifiable transparency component, right? You can offline ask what it's running and see what it gives you, and then online you can double check it and then actually submit that data. The next thing that they discussed, right, no privileged runtime access. I kind of showed here in this diagram. This is where an SRE could SSH into the machine. Now the SRE can't SSH into the machine. Great. Conceptually, that's what they do. In practice, it's a little bit more difficult. Enforceable guarantees, when we talked about that briefly. If they don't want to store data locally, then they shouldn't have a disk. And so there's lots of examples of this throughout their system where there's no disk because they don't want it to be. But this is another example. Like it's stateless. You shouldn't have to have disk. Now there's some temporary disk, and we'll get into that. But the temporary disk is encrypted with a key that's thrown out at boot, so they can never recover the disk if they were to restart the machine. Okay, so there are 6 technical components, and we're going to go into each one. And then I'll discuss some of the things I've learned, hopefully give you some pointers. Again, I think these are some interesting tools that are becoming more accessible that you may encounter, particularly if you're dealing with any sort of data privacy, even if it's for an enterprise customer. So the first component I want to discuss is oblivious HTTP. It's a new spec that came out that is essentially like a formal version of Tor, if you're familiar with Tor. And it essentially says, I'm going to send, let me just show you. Here's the old way, right? You make a bunch of requests to the server sees where the data comes from. Very clear in this example. Client A sends some data, client B sends some data, client C sends some data, and you know the source. So oblivious HTTP first says, well, send all your data to a third party, and then that third party will send the data to the server. And now that server doesn't know the true source of the data, it only knows that it came from the third party. But there's a big problem with this, and that is the third party should be untrusted. Otherwise, the third party can just see all the data and send it on anyway and send the true source. So the way they overcome this in the spec is that you encrypt the data, using the public key of the server, and then you send it to the third party encrypted, so the third party can't see any of the data, and then it flows on. And this is a formal spec. It's available. There are libraries out, and you can pay Cloudflare and Fastly to offer this essentially laundering service, so to speak. Again, like think of it almost like a formal Tor, but a standard HTTP spec. Okay, so I've built this at Confidence Security. The first thing is that streaming plus encryption is incredibly difficult, incredibly annoying, but streaming is fundamental to an AI workload. That said, we have an open source library that's going to be released soon that implements the spec. It's very new. It was developed by Apple and Cloudflare together. But this part is very hard. There'll be libraries to fix that. The second thing that I learned is that you must use exactly one certificate. I think I said here that the server has a key and the public key is given to there. That cert needs to be only one. Otherwise, you could issue, each client could be issued a different cert and encrypt the data, and then you would know the source of the data anyway. Cloudflare and Fastly are awful to set up. They don't really have these as formal products. It's like a kind of like a promise that they'll help you out, and you can pay them a lot of money to do this. I found one service that does do it. It's oblivious.network, and they're super quick. They're built on top of Cloudflare anyway. So, and this is key in Apple's, just to be clear, this is key in Apple's vision that Apple can't run their own third-party service because then they could collaborate to figure out the information. The whole point is to raise the bar. So you put some trust into Cloudflare and Fastly's reputation that they're not giving the data to Apple to actually tease out who it is, because Apple doesn't really want to know. Okay, next piece, blind signatures. Blind signatures is a way to digitally sign something without seeing the content. And then later, once you see the content that's signed, you cannot link the signature back to the person who got it signed. Just a little complicated, but hopefully this explanation will help. And I'm going to just give a brief analogy for blind signatures via shipping. So when you want to ship something via UPS or whatever, you pack it up, you take it to the store, you pay for it, and you ship it, right? It's the standard flow. So like that's what I just said. Box it up, you go to USPS, you show them your credit card and your ID conceptually, and then you give them the package. That's great, but this means that UPS can link the package to your ID. And blind signatures is an important component so that when they're doing auth, you can stop that linkage from happening. So let's design an anonymous postal service. And this is essentially how blind signatures work. First, a couple assumptions. Let's assume that USPS cannot ID humans. They can only ID boxes. So like when you show up, they can't ID you. They can only look at your ID and your credit card. The second is that boxes are unique and that you can ship in standard boxes. Doesn't really matter. Okay, same flow, but there's a couple extra steps to make it anonymous. The first step is after you box up the package, you shrink wrap it in some sort of piece of plastic. Then you go to UPS and you show them your credit card and your ID, and UPS signs it. And when they sign it, they cut through the shrink wrap with their signature. You'll see in a second why. The next thing you do is you go to another UPS. You give them the package, but you remove the shrink wrap before you give them the package. So now they receive a package that's signed, that someone officially at UPS has said, yes, this package has been paid for and available to ship. But now you don't have to show your ID or anything like that. And then UPS checks the signature is valid, and boom, you're able to still ship the package. In this case, you had this two-step. You showed your credit card and ID to one person, and then you just gave the box to the other person. And because you removed the shrink wrap, they can no longer tie the two boxes together. That's the funky part. It's kind of a funky piece of math, but it essentially is a way of HMACking something, or if you're familiar with standard signatures, where you can change what the signature looks like, but still prove who the signer was. Okay. This is actually really easy to use. There's a Cloudflare library to do it. But one challenge is it inherently makes usage difficult to track. So if you're trying to do auth users through your system using this and then track their usage, you can't. So that's annoying. And again, you must use exactly one certificate for signing and post it publicly. Otherwise, again, you could create end certificates for end users, uniquely sign them all, and then be able to trace them all back. Okay, and once we've worked through these primitives, I'll put them back on that map, and we'll get a sense of how it all comes together. But these are the two critical pieces to anonymization, right, which is about non-targetability. Okay, the next piece I'd like to discuss is remote attestation. Remote attestation is essentially, conceptually, again, the client asking the server, hey, what are you running? And the server says, here's what I'm running, and I've signed it, proving that I signed it, not someone else signed it, and here's a public key. And if you trust these claims, you can encrypt the data with this public key, and only I'll be able to decrypt it. That's the most important part, assuming you trust the claims. And assuming you trust that public key is associated with the server, then you could encrypt it, and only that server would ever be able to decrypt it. So that's essentially what Apple does, right? Your iPhone has a bunch of, that makes the request, says, what are you running? It comes back with a bunch of signed claims. The iPhone decides to trust them or not trust them. And if so, then it encrypts your AI request only so that specific machine in Apple's infrastructure can decrypt it. There is no easy off-the-shelf way to do this. OHTTP, the previous thing, and blind signatures are like relatively standard libraries now. Remote attestation is not there yet. You got to build it yourself. You may think that you can go use Intel's libraries to do this. You should not. Intel has a whole system for doing remote attestation of their CPUs and the operating systems that are running on top of them. It does not work well, and then you spend $50,000 to $100,000 and discover that it's not reliable. So that's recorded, isn't it? Oh, well. Okay, so the other important concept here, when we talk about attestation, and some of the viewers may realize this, there's a difference between when you attest, when you ask what are you running, to when you check it, when you check the claims that were sent across, to when you actually do the inference. And there's a big risk in this, figuring out how to make it work so that when you ask what you're running, and when you checked it, and when the inference happens, it's still running what they claim to be running. And there is a way to do that, and that involves the next topic, which are TPMs. But this is a very important concept if you're ever doing some sort of remote attestation where you might be volunteering to your customers what code you're running. You know, that's the time of check versus time of use, classic like security bug. And then there are many components you end up needing to attest. You'd think it's just like, prove to me exactly what software you're running, but you need to prove that the GPU is genuine and not hacked, the RAM is encrypted, that the TPM is legitimate, that the network interface card is legitimate, that the disk hasn't been manipulated, and then standard things like the boot and operating system. And all of these things are included in the signed claims. So you have to believe that all of these are valid, that they're genuine. The way that you know they're genuine is that all of these vendors publish certificates of genuine hardware, and then you go and verify the certificate chain as well as the signature of information they give you. Okay, that's conceptually how remote attestation works, and we'll have plenty of time to get more into it. Next thing is the secure enclave. This is unique to Apple. We have something similar available to all of us, but the secure enclave is a special piece of hardware that Apple's built. It's in all of our iPhones and our Macs and all of the other things. It's essentially a separate small chip running a separate operating system, which is where all of your private keys are, right? So when you have like phone encryption keys and other things, like all I have to do is nuke the secure enclave and then your phone can never boot again, essentially. So this is a critical component. When we were talking about in remote attestation, this public key, the private key resides in the secure enclave. So I'm not an expert on the secure enclave. I'm not going to profess to be. This is just a special piece of hardware that enables it. And this is really where all of the trust centralizes, right? So if you trust this official piece, then you can start trusting the pieces above it that rely on it. So special hardware that runs a separate secure OS. Secrets cannot be seen or stolen. So if your system were hacked, they can't access the secrets that are stored on this separate chip. This is the system that verifies that the boot is like official and that's tied to your device, that it's not running like hacked software. This is where those storage keys are kept, encryption keys are kept, And they're all here so that if you need something decrypted, you actually don't get the secret key. It does the decryption for you. Okay. Since there is not an analog, what I learned trying to build an equivalent, Trusted Platform Module is the closest public equivalent. There's a spec for them, started in 2009. Now there's the 2.0 spec, which I think is like finished in 2015. It's awful. I mean, it's really cool, but there's like essentially one document that's 200 pages long. It's just a PDF, and it just lists these arcane commands that you can like hope to understand. Cloud service providers have virtual TPMs, right? So if you have if you buy a physical box on newer Intel chipsets, they have TPMs, but on the cloud they don't have them because they're virtualized. So they have virtual TPMs, which is a whole nother level of trust. Now you're putting your encryption and keys in a piece of software that Google wrote that you don't get to see, that offers the same functionality, but it's something I learned. And the key with the TPM, I talked to you about, it's pretty simple. It's just a place to store secrets. And then it also interfaces with a bunch of Linux features, such as the integrity measurement architecture, DM Verity, DM Crypto, DM Integrity. I know you may not know these things. It doesn't really matter. And these are the things that interact with it so that you can build, it provides the trust layer, and then they give it more information. And when you do an attestation, you actually go to the TPM and say, what are the values in the TPM? And the TPM essentially signs them and says, yep, they're legitimate. And then if you trust the TPM, you should be good. This is all an exercise in moving around trust, if this hasn't become clear to the listener. Okay, the transparency log. This is the fifth piece that Apple uses. The transparency log is what facilitates security researchers verifying the claims. It's essentially a tamper-proof, append-only public record of software packages. Let me show you what I mean. It's actually a very simple database. Essentially, imagine I'm Bob and I need to release a piece of software to you that you're going to download. I just write it to this transparency log. I hash the binary. Maybe I link to the source code, and I say, I'm official, I'm Bob, I'm releasing this binary. So the benefit this provides, if you're a user of my software and you get the binary from me and you hash it and it doesn't match what's in the transparency log, then you know that the system's been compromised because I didn't officially release it. So this is how the security researchers who are verifying Apple's claims about private cloud compute can develop trust in the software binaries. So every time Apple updates its private cloud compute, it publishes the hashes of all the binaries to this log. Then the security researchers can go through and look at these binaries, be like, oh yeah, this is legitimate, this is not, this is doing what they claim that it's doing. Great. When the iPhone receives claims that this software is running, the iPhone can trust it. And the security researchers, this is the offline versus online, right? So you check that the remote attestations match what's in the actual log publicly available. There should only be one log that's publicly available. And if anyone ever sees something that's not in the log, they know that they're hosed. Simple concept, but the important part is that essentially everyone's agreeing to it and reporting the information that they are intending to use in advance. So what I learned about implementing this, I didn't have to build it. There are two projects available right now, SigStore and SigSum. And if you're familiar with some of the secure supply chain work, Salsa, SLSA, and some of the other things that are on GitHub now and other places, SigStore, I believe, is the project that uses this. The hard part is deciding what parts of your system you want to put in the log, right? I could say, I'm running a secure VM. Here's the hash of the entire VM and put it on the log. That becomes very difficult to verify. Every time you make one small change to the VM, you have to put a new entry in the log. And then someone has to go through and figure out what changed and trust it. So you want to kind of balance how you break down what you put in the log. You could put down in all the binaries. You could put down all the Linux, dependencies in there. You could put down all of your config files in there. There's lots of different ways to skin this cat. I've never said that before. Okay, the last piece is secure boot and hardened operating system. This is relatively straightforward security thing. You probably all heard of it. It's just making a limited attack surface, and making it run exactly what it claims to be running and nothing else. There shouldn't be many ways to change how the system behaves. For Apple, the most critical piece is their boot ROM. And I would usually point over here at the boot ROM, but that's not going to work. So the boot ROM is a hard-coded, read-only thing that starts the whole boot process that's burned in during manufacturing. And that is the piece that verifies every subsequent piece, kind of accruing it. So the boot ROM verifies that the low-level bootloader is signed by Apple and legitimate piece of software. And the low-level bootloader verifies that iBoot is set, right? And it grows and grows. So you get this secure boot, and then Apple's running a pared-down version of iOS in its public cloud. And so, and like a couple other items here, no dynamic code execution, you can't SSH into this machine. There are no extra drivers or firmware, right? Linux is a lot different because it has essentially everything under the sun. But Apple's stuff is really pared down, and all code must be signed. So when you get the remote attestation with all of these signed claims are signed by that secure boot chain that I talked about. So if you trust that Apple's boot chain is secure, and it says it's only running this code, then the iPhone says, okay, great, it's definitely running only this code, and this code is on the transparency log, so great, this is an official publishing. Of course, someone could be hacked and publish something false to the log, but great. Okay. For folks who might be interested in hardening an operating system because they want to offer these stronger claims about what their software is or is not doing, unikernels aren't really feasible. I don't know if some people have heard about unikernels, but they're becoming popular as a way to like run things faster and more simply. But they don't really work for the complicated workloads with GPUs and all those other things. The second thing is if you want to lock down an operating system, one of the key things is you remove all shells because the shells are a great way to escape. But a lot of things use a shell, so that kind of sucks. If you're locking down an operating system, the easiest way is probably to use SE Linux if you're familiar with that kernel module that allows you to specify the exact syscalls and level of privilege that an individual process can have. Apple's system is a little different than this. Of course, they have a different operating system, but if you were to do this, that's what it works. And then there's a library or a system out there called Yocto, which allows you to build custom images. It's a very steep learning curve, but once you do this, you can have a very pared down image. Like a base Ubuntu image is incredibly insecure. For good reason, so they're trading off support for security. Okay, so this is where we left at a high level. Now I'm going to integrate those 6 pieces we just talked about. And I'm kind of getting nods, so let's just keep going. Okay, the first piece, anonymizer, OHTTP. We talked about that. We slap that piece in, Cloudflare and Fastly run the traffic through them. And by the time it gets to the AI engine, we just know that it came from Cloudflare and Fastly. We don't know that particular user it came from. Auth. So auth is done via blind signatures. So the way it works is the iPhone goes and says, hey, I'm Jonathan. I want to make an AI request. The auth service says, yes, you're legitimate. Here's some tokens that are signed with a blind signature. I receive those tokens, and I essentially remove the shrink wrap that we talked about. Now the tokens look different, but they're still official. So when the AI engine receives one of those tokens, it's like, oh yeah, this is a legitimate request, but I have no idea who made the request. The next thing I'm going to put in here is formally defining remote attestation. So the iPhone makes a remote attestation request. The AI engine responds with a set of claims about what software it's running. And what the iPhone does is say, hey, try to decrypt my data and run the AI. And this is very subtle. I changed the language here. What this means is it's specifically described as the iPhone commingles the attested values. And again, attestations are just hashes, really, right? They're hashes of everything. And it commingles these attestation hashes with the actual encryption. And so what this means is the AI engine, if it changes the software it's running, it cannot decrypt the data that the user submits to it. We were talking briefly, or I talked briefly about time of attestation versus time of verification versus time of use. This fixes it so that right when it's used, the values that the AI engine is using, that it claims to be using, matches what it attested to earlier on. The next two things that I just put in here doesn't, the secure enclave is the key, and the secure boot and whole system is the lock. Essentially, we could go in depth forever just on those things. PhDs have been written on those things. So the critical thing is before 4 happens is that transparency log check. So the iPhone says, hey, what are you running? It gets back the claims. The first thing it does this async for what it's worth. And it says, hey, are these attested claims on the transparency log? If they're not, I'm just not going to trust this AI engine at all. And of course, in theory, the AI engine should only be running what's on the transparency log. And if it's running something else, none of the system works. Okay. Couple areas for gaps in private cloud compute. The first thing is that you put all of your trust in one party. Right? Apple could be setting all of the private keys to one. Right? Apple could be burning in insecure things in their data centers. You can't know, right? They wrote the code for your iPhone and they wrote the code for the servers. That said, I think they have a strong incentive to do things right, and I think it's a very impressive system, but it still puts all your trust in one party. The second thing is not all the source code is available. There's no guarantee they didn't share their certs and their private keys with people. And it's relevant to this audience is if you ever want to meet something with this level of security guarantees that I just discussed, you can't yet. Maybe Apple will eventually open it up to third-party developers, but they're definitely not going to open it up beyond their devices, and their ecosystem. That's a big limitation. And then you're probably asking, well, this seems like a great, amazing thing. There's got to be some trade-offs. And the answer is, of course, yes. The first is if you want really low latency AI workloads, you're not going to get that. You have to go to Apple data centers. It's incredibly operationally complex to run. If you can't SSH in the machine and see what it's doing, it's going to be impossible to figure out bugs. The compute costs are only a little bit higher. Actually, there's some extra encryption. There's like 4 layers of encryption. We talked to oblivious HTTP and the encryption to the machine. So that's not too bad. There's no way to do usage tracking. I noted that before, but because everything's anonymous, I have no way of tracking like how much money I spent on AI and whether I have a user who's like essentially abusing my system. They do have a fraud and abuse system, but it's not as good as like full usage tracking. They just kind of catch weird usage. You can't do fine tuning, no custom models, no third-party developers, like I said, and the client libraries are very complicated. As I've shown you, like the iPhone went to making a simple request and getting a response to doing blind signatures and then doing remote attestation, then going to transparency log. And you need to do all of that and make sure none of those fail, because otherwise you have a real bad client experience. Okay, so what can I learn from all of this? Maybe what you're asking, why am I here? The answer, I think, is there are really actually 8 components, and I'll talk about the last 2 in a second, that you may encounter in your work, or you may be interested in using yourself to offer stronger privacy and security guarantees. Hopefully, I gave you an intuition for each of these and how they integrate in PCC, but also at a high level, just what they can do. And I'm happy to talk about to anyone if they're interested in using that themselves, giving you more pointers, libraries to use. The last 2, we talked about confidential computing. What's actually interesting is Apple's system isn't confidential computing in the classical sense. All of these other things are kind of like wrappers around. It gives you confidential computing, but we historically thought of confidential computing as an encrypted RAM, essentially, where inside of it you can like do things that no one can see. But if we wanted to do it, rather than Apple, we would use a confidential VM. And the cloud providers offer confidential VMs. And these confidential VMs have those virtual TPMs attached to them. And these give us a guarantee that the cloud providers can't see the data. That's not something that Apple's concerned about, but the second that you're leasing compute from someone else and you're trying to be private, you don't want Google or Azure or whomever to see it. Side note, if you need a GPU in a confidential VM, AWS doesn't have that yet. So only Azure and GCP support it. The reason why is that the confidential primitives that Azure or AWS uses is custom built, whereas Azure and GCP use Intel and AMD systems, which work with PCI really well, whereas AWS doesn't yet. The last thing that's unique to us that Apple doesn't do is that this can all be open source and you can have reproducible builds. So I talked a lot about the hashes of the binary, the attestation of what the binaries are running, but they don't provide all the source code. So you kind of eventually you can exercise the binaries, but you don't actually know what's inside of it. If you were building a system with increased privacy and security guarantees, you would have a reproducible build system. You would give the source code out and say, hey, this is what builds to this binary, and this binary is on the transparency log. So you could develop additional trust in your system. Okay, and I'll just end with, we're building this thing. If you want our benefits and you don't want to build this all yourself, we have a provably private area inference engine. It's the same as like any other inference engine out there. It's standard chat completions call. And we can make all of these cool guarantees about prompts not being logged, not being used for training, not being used for third parties, etc. And that is about it. I can wait for questions.